Hey, good afternoon, everybody. Thank you for coming to JavaScript for Science. Before we begin our presentation, I want to emphasize that although we're going to be talking about JavaScript and some web-based examples today, that the stuff we're talking about in this presentation is not specifically isolated to JavaScript and this particular language. So to begin, my name is Angelina Fabbro. I'm Angelina Magnum on Twitter, and I work for Mozilla. I work on Firefox OS there, but also I spend a lot of time teaching people how to code. And before that, I got a bachelor's degree in cognitive science, and I worked in the software industry in a variety of capacities.
And I'm Bill Mills. I'm a nuclear physicist currently working for Triumph. At Triumph, I'm currently responsible for the user interface and user experience design for the Griffin collaboration. Before that, I spent a number of years writing analysis software for the Atlas collaboration on the Large Hadron Collider at CERN.
All right, so we're here to talk to you guys today about a particular thing. And that thing is that we would really, really like you to help us change the world. And I know that when people say that, they, like you get this idea like, okay, one person can't actually make a whole lot of impact. But we've discovered a few things, a few patterns with the natural sciences in particular and their programming practices that we think that the people in this room probably have a lot to offer and help with that. And with your cooperation, we can actually do better science, and thus that does make the world a better place. So, real talk.
So, I want to start off with a bit of a confession here, a little bit of real talk time. Right. Everyone here is familiar with Moore's law for semiconductors and integrated circuits. It suggests that the number of transistors on an integrated circuit doubles every couple of years. Well, while I worked at CERN, I noticed a similar phenomenon going on with our detectors there. And what happened from that, it can be summarized here. What I have here is the number of data collecting sensors per experiment in CERN's big flagship experiments over the past 30 years. So in the early 1980s, we had an experiment called UA1, and there was about maybe 10,000 data collecting channels on UA1. Fast forward to today and the Atlas experiment on the Large Hadron Collider, and Atlas has over 100 million data collecting sensors. The scale and complexity of these experiments is skyrocketing. It's grown by 4 orders of magnitude in only 3 experimental iterations. And yet, we haven't really kept up with the best practices from the software engineering world. And in so doing, we've amassed a tremendous technical debt. One thing that CERN kind of got right with these experiments, because they had to, was that as their experiments scaled up, they developed some tremendous data visualization techniques. I mean, as they were required to for an experiment like Atlas. So any member of the Atlas collaboration would recognize this plot as having the fingerprints of the Higgs boson in it in an event we recorded last year. And yet, despite this leap forward in experimental complexity, and despite our work in good visualization for our experiments, in the 5 years that I wrote analysis code for the Atlas collaboration, I never received one single code review. At all the software meetings that I went to every week for that experiment, words like scalability, portability, maintainability, usability, all the abilities of software development weren't part of the discussion. They just weren't on the radar of scientists developing there. And there our technical debt began to mount. As a result, I believe that over time, big physics has built some big monoliths of single-use code. Meanwhile, while this was going on in high-energy physics, in my other field, nuclear physics, we built a web app called Midas, that looks a little bit like this, for monitoring and controlling our experiments in real time. And one thing that I was always really sort of impressed with and proud of about Midas was that this was a web app built in the mid-1990s. I mean, web app, I don't think web app was a word in 1994 or 5 when this was first being developed. But nevertheless, physicists said, this newfangled internet thing, this is the way to bring our experiments, to make them more portable and more usable into the future. And so we jumped on this bandwagon, built Midas to great effect. We've been using it on many experiments ever since. But that was 20 years ago now. In the intervening 2 decades, people that work on the internet and develop web technologies have made brilliant beautiful advances in things like information design and information architecture, usability and interactions. And yet, Midas is still exactly what it looks like. It's a table dump of the thousands and thousands of parameters that go into a modern nuclear physics experiment. We haven't integrated all those advances yet. We're lagging behind, and the gap between the natural sciences and software engineering has grown, and our technical debt begins to mount.
So Bill and I met each other just a little over 2 years ago, I think we established the other day. And when we met, we realized that we had things that we found very fascinating about the other. I mean, I come from a software engineering background and cognitive science, and Bill comes from a physics background with both nuclear and particle physics, an area that I really did not know a lot about, and similarly, Bill did not know a lot about what I was doing. So we ended up becoming friends and hanging out and having conversations. And I remember the first day that this discussion between us started. I was hanging out with Bill, and he said, oh, hold on, I've got to go do something. I got to go jump into a terminal. I got to go look at some code. I was like, oh, cool. What are you working on? And so I peer over his shoulder, and I look at a file, and I see that he's on line 13,000 of 50,000, and there's this big mass there. And so I say, hey, Bill, are you really on line 13,000 of 50,000? And Bill, completely naive, turns to me with these big eyes, yeah. Why? What's wrong with that? And I'm like, okay, we've only been friends for a really short while. I don't know if this is the time to be all right, serious time in our friendship and relationship. It's time to talk about software development practices. Thankfully, Bill is an extremely receptive individual, so we obviously did talk about those things. But the thing is, really, the point to be made here is that Bill just didn't know better. When Bill got into his PhD, he had maybe, I think, one course in computing science as an undergraduate, which is not sufficient knowledge and expertise to build a system of the scale that he was trying to build, or the scale of the simulation that he was working on. Sometimes you just don't know any better. So now let's actually take a little bit of a look of some of the examples of things that we found in actual production code from the domain of physics. So I apologize if this is a little bit small, but we wanted to really capture what's going on here. So the first thing you can note is that there's this pyramid of doom going on. We've got a really high degree of nesting, and usually code with a lot of nesting like that, it's usually pretty bug prone because it's very hard to keep a mental model of what's going on with this kind of a structure. The next thing that you'll note, quite generously, there's one comment. And this is sort of an outlier. The rest of the examples, there's no comments. And the thing is, it's also really ambiguous. Map the data from the JSON P store, okay, I'm with you so far, to the DAC object, whatever that is, that's some domain knowledge thing, summing rates as we move upstream. I don't know what that stream is. Maybe they mean as we move through the JSON P file. I don't know. And then, of course, all of this is very terse. And I think what's going on right here, this dot data keys index of P key equal to -1, I think that's checking if something's out of bounds in the array. And the person that wrote this code was Bill. So this is an example of something that I'm pretty sure if we spend some time with this code, we could refactor it to be a lot more readable, a lot more maintainable. So the next example here is a bunch of calculations across a number of axes. You've got a z variable, an x variable, a y variable. But actually what I want to turn your attention to is over on the right-hand side here. This is from an editor in Sublime Text. It does a really good job of giving you sort of a relative idea of where you are in a file and how long that file is. But it might be a little hard to see, but there's actually a pattern here. You see this shape, and then you see this shape again, and you see it again, and you see it again. And can you guess what's going on here? Yeah, that's right. It's copy and paste. Yeah, so Bill got this code, and he was someone else wrote it. He was responsible for refactoring it. And this was done 16 times. So the person that wrote this code did not maybe know or did not understand that they could take these calculations and put them in a function and maybe call that function 16 times rather than copy and paste. Another few things about this is from talking to Bill, we know that these calculations are calculating some points along an axis, like z, x, and y, but there's no comments. And even though Bill is refactoring this code, we have no idea what this is actually calculating, to be honest with you. We know that good results come out the other end of the code, but we actually don't know what this is doing. And this is often true for a lot of inherited code in physics that someone can be given. Like you're given like a chunk of code, yeah, so-and-so already did a simulation, and you get stuff like this. Now the last example that I want to show you is my favorite. We've got that whole thing that was going on with Bill here. I think, I don't know what line we're on, but we're clearly at line 13,480 of some file. And you'll notice at the top that we're in a file that's got a C extension, so it should be C. But really what we're looking at here is JavaScript. This is an entire string in C that produces JavaScript. So the person that wrote this knows JavaScript because like when this spits out, it runs properly. But they chose to print it out as one giant string in C for reasons that are sort of unclear, but not entirely. I mean, this person was clearly the most comfortable in the domain of C and probably C++, and that's probably where they did most of their simulations. Sorry, one of you in the audience has the most horrified look on your face, and I find it hilarious. That's the right reaction to this stuff. Just like, I'm like, whoa, I knew this was going to be heavy, but, and so you can see that, when you've got a hammer that's got the label like C or C++ on it, everything starts to look like a nail. You start trying to do things like put the square peg in the round hole or just circumvent the system entirely altogether rather than learn the skills that you need to adapt to the environment, like maybe creating an interface in the web browser. So this is not really what you want to be doing. And so we've discovered from talking to our peers in the scientific community, and I have other friends than Bill that have gone through grad school in other areas like ecology, and even in engineering. And it seems to me that there's an impetus to write unmaintainable code. So imagine that you're a grad student and you're trying to get yourself towards the end of your PhD. You probably think that you're writing this code, you're going to write it once just to prove the results of your theory and your calculations. And that probably no one's ever going to use it again. But that's often not the case. These grad students will go on and graduate. Probably they'll go to a postdoc or something else at another school, but their supervisor will know about that code. Their supervisor hasn't vetted that code. And when someone new comes that is maybe in the same area of research, they say, okay, so-and-so, Bill was here. You can use his code, and here's a starting point. And this is really dangerous because that person is given a big piece of tightly coupled monolithic code, and it may inspire them towards really problematic development practices and perpetuate this cycle. Another situation is that when you're in the academic world, there's a whole lot of pressure to publish against deadlines. Whether it be for a conference or just for a paper in a publication. I mean, that's what happens in the software industry as well. I mean, sometimes your boss says, okay, you've got to stay late on Friday night, and we really need to ship this iteration of our product. And when you're under that time pressure and you don't have time, what do? You don't write the best possible code that you know how to write. You get in a hack so that it's fixed on production. The same is true for this code in physics. When they need to publish a paper, or when you need to publish a paper or be ready for a conference, you just get it out the door so you can say that your simulation works. And the problem is when you create software this way, when you just keep adding hacks, you don't comment, and you create these tightly coupled monolithic pieces of software, refactoring ends up feeling a little bit like this. You don't have the expertise to go through a big piece of code, and you just kind of cut and paste and move things around and nest and nest and nest. And then once it works, you were so frustrated to begin with, you just don't touch it. But the good news is not all lab science the same. There are a few labs out there that actually do understand that we do need maintainable software, and we do need good tools for scientists to have maintainable experiments and do good science.
So for the past year now, I've had the privilege of working for the Griffin Experiment at Triumph. And the Griffin Experiment is a new gamma ray spectroscopy experiment, totally cutting edge and ahead of its field, coming online at Triumph next year. Griffin's physics goals are threefold. First, we will be exploring the R process, which is how the heaviest elements get made in supernovae. We will be examining fundamental physical symmetries as a cross-check mechanism for high-energy experiments going on at labs like CERN. And also we'll be continuing Triumph's long-standing tradition of contributing to the study of nuclear structure with this array of gamma ray detectors and their auxiliary apparatus. In addition to our physics goals, we have a number of computing goals for Griffin as well. First and foremost of them is that both I and the management of this experiment see Griffin as an opportunity to take a step forward in terms of how physicists interact with their code and how they build user interface and user experience machinery for interacting with their experiments. So over the past year, I have been developing a web app to meet this goal, with the goals of making an interface for Griffin that requires as little domain knowledge as possible. See, there's going to be groups of scientists coming through Triumph every week or 2 weeks to use this apparatus. They cannot spend a long time learning how to use this thing. So we want to use the best of web technology and interaction design to make this as simple as possible. So I'm going to walk you through a few of the features that I produced for Triumph. And while I do so, I want you to keep in mind two things. First of all, how we solved these problems before was via that table dump that I showed you. So contrast this to having everything just in a bunch of numbers in a list. And the second thing is I want you to be absolutely brutal and critical. Think about how you would have solved these problems. Think about how, or what you think is still lacking with the solutions that I've come up with. Because, I mean, I'm a physicist just kind of swan diving into user experience design. I'm sure experts and professionals would have even more to say about these ideas. So let's dive in here. Here is my web app, and it serves a whole bunch of different purposes for Griffin. One of the main assets that it produces is these skeuomorphic representations of our detectors that let us see what these detectors are doing in real time at a glance. It also provides a high-density view of our high-voltage information that allows us to monitor the many hundreds of high-voltage channels we need to run these apparatus all at a glance, so that we can see, sort of easily notice when one of these channels might be going wrong, like we have over here. We needed a data throughput monitor, which I have here. So these are like my data collecting nodes, and it shows how much data is getting pushed up to my master here, so we can keep track of how much we're writing to disk all at once. We've got a bunch of hardware monitoring assets for our atomic clocks and our voltage crates, and a bunch of interaction design objects, which I'll take you through in more detail later. This is, like, the purpose of this is to, like I said, monitor in real time for the sake of debugging and troubleshooting everything that's going on in this experiment. And so, like I said, I'll go back to these skeuomorphic detector representations here.
So what we're looking at here is Duscont, and Duscont is a collection of sensors. It's a big round thing, actually, which is why this is round here, and it detects neutrons firing, pardon me. And so there are about 70, there's 70 detectors or sensors here. And at the bottom here, we've got a scale that shows from 0 to 1 kilohertz there, yeah. So all of the colors that are in sort of like the warm range are firing between like 0.3 and 0.6, which is about 300 to 600 events per second. Now, as Bill was saying before, this information basically came in a giant table that was a data dump. So if something ever went wrong with these detectors, you would look in that table and you would of course find probably a 0. But the difficult thing with those table dumps is the information was not always necessarily organized in a way where all of those zeros might come together as a clump. You would have to have domain knowledge to know, to look to that table, to see the zeros, and then you have to go through the table, find all the zeros, and figure out what that meant for where those were in the detector, like which sensors were actually malfunctioning. By creating this skeuomorphic representation of the detector, we can easily see at a glance where the zeros are and that this portion of the detector actually has a problem. Now, the interesting thing about this is that the context preserves a lot of information, and it makes it a lot easier to see what the problem is at a glance. Now, what I find fascinating about Bill's implementation here is one day he came to me and he said, Angelina, can you help me debug my JavaScript? And I'd been teaching Bill JavaScript before he had this job, and I was like, of course, sure, I will totally help you debug your JavaScript. And so I hadn't really played too much with his web app. I'd left him to his own devices, and I right-clicked on something that I thought was going to be a DOM element and went to go inspect it in the browser. And instead, I found that Bill had done everything with like 3 canvases. So where I was expecting a bunch of DOM elements, actually Bill had used a bunch of canvases. And I asked him, I was like, well, I know you understand the box model, and I know you understand HTML and CSS and JavaScript. Why did you do everything in Canvas? And the answer was very simple. Well, I was under some time pressures, and I just wanted to get something made, and I just didn't know how to make a hexagonal div. And I was like, okay, that seems reasonable. And so he discovered the canvas object, and that he could control every pixel written to the screen or in that canvas object, and that he could actually draw out the skeuomorphic representation and also deal with the changing state of the experiment in a really elegant way. And on top of that, so he implemented this in Canvas, but he also went on to implement his own event listeners and also his own tooltips as well, which on one hand I found totally ridiculous, and on the other hand I also found totally amazing that like I just kind of left him alone and this is what he did. But this is a bit serendipitous, right? Like on one hand we can know in a situation that like if we leave someone to their devices, it might not turn out terribly well. In Bill's case, with the number of elements that he needs to represent and their changing state, doing this in Canvas probably in the end ends up being more performant than juggling a bunch of DOM elements and dealing with their state. So for Bill's purposes, this ends up being actually probably the better solution. But you can imagine how like this could have gone sideways were it another situation or another technology or somebody just fumbling around and hoping to get it right. And so the interesting thing in addition to that is, let me pop over here to Shark. We're dealing with so many channels of information. Now, this is an exploded view of another detector. Of course, it's got the same sort of firing rate representation. But actually, these panels are averages of detectors within them. So we've got kind of like this long box-like thing. And then on the ends, there's like these circular things, which is really the technical way to explain it. But if you actually click and drill down, you can see that there's actually even more detectors in there. So Bill has done an excellent job here of creating representations so that scientists can get at exactly the information that they want and knowing exactly what component in the experiment is producing that information without having to fumble with some sort of table.
Okay, so as Angelina has walked through here, there's a whole lot of information design problems we had to address in Griffin. And I mean, there's still plenty more, right? I mean, doing a 70-channel detector like Duscont like this was sort of no big deal. But when you move to something as complex as Shark, I mean, it's kind of tough to tell what's going on here. Someone with real experience in user interface design could do even better here. But anyway, it's not just UI and UX problems that we have to deal with. We also have a lot of interaction problems to solve. So in any one of these experiments, you always have to set up a simple experimental cycle that you're going to run through while your experiment runs. So how these experiments are typically configured is there'll be a big spherical array of detectors arranged around a point where you're going to want to have your source. And how you put your source in the middle of those detectors is there's like a movie reel, like a movie tape, that you can move into place in the middle of your detectors. Then you turn your radioactive beam on, and you implant a bunch of radioactive goop on that movie tape. Then you turn your sensors on and record data. And you repeat that cycle a million times for as long as you want to collect data for. Simple enough. But before I developed this web app, what you had to do to implement something like that is that each of those actions would have like a little bit pattern. And then by hand, for some reason, you had to take those bit patterns and add them together, turn it into a hex number, take that hex number, and put it in that table, that big table dump of instructions that run this experiment. Now, I mean, I suppose that's not very complicated or very hard, which is why it survived for so long, but it's also completely unnecessary. There are so many good tools for interacting with a piece of software that being stuck in the 1960s like that just seems a little silly. So, I mean, what I developed to solve that, I can re-implement the exact cycle I just described with this interface. I can clear my memory, there we go, and then I'll move my tape into place, and then maybe I'll implant some radioactive source on my tape, and then I'll turn my detectors on. There we go, I've made an experimental cycle for Griffin. It took like 10 seconds, and all I had to do was use my intuitive notion of interactions that I've got from just general fluency with computers and smartphones and stuff. No special domain knowledge is required anymore. And that's one of the main goals for interface design in the sciences, is to suppress that domain knowledge, put as much of it in the background as possible so we don't get distracted by it. Because that's what domain knowledge ends up being, particularly for new collaborators, is a distraction that stops us from making more progress in the sciences.
All right, so I'm going to talk a little bit about the sort of cognitive biases that really get us in the way of ourselves and in the way of achieving things. So in 2012, I organized the Vancouver chapter of the International Space Apps Challenge. And so for the International Space Apps Challenge, what NASA did was they said, we want to engage people who are not necessarily professional scientists. We want people from interaction design, user experience design. We want software developers. We want to get them together for this weekend code-a-thon or hackathon. And we will pose a number of challenges for them to solve. And then we would like to see the best solutions, the winners of each one that, that the judges thought were the best. And then they would go on to sort of like an international level of voting. And projects that were particularly interesting and caught the eye of NASA, and they were released open source, NASA would then sort of like draw either inspiration or use their code. And that happened in a number of instances. So in the Vancouver location, we had a fairly reasonable turnout for like a code-a-thon, hackathon kind of event. It was definitely skewed, like the attendees are definitely more skewed towards like academia. Like we got a lot of people in computing science, and disappointing for me, not as many people from the software industry. One of the groups that won did a really fantastic, the group that won did a really fantastic visualization of the aurora borealis in real time using like a data feed from NASA, and it was fantastic. And when they were talking to me, they said, oh yeah, last night I was talking to my friends and they were asking me all these questions about what we were doing at the NASA Space Apps Challenge. I said, oh, well, what do your friends do? They're professional software developers. I'm like, okay, well, why didn't they come? Oh, well, when they heard it was going to be science, they thought that they didn't have the necessary skills or knowledge to participate. And that was just really disappointing for me, because even if you don't have the necessary domain knowledge for physics, that doesn't mean that you can't learn a little bit, and it doesn't mean that you can't contribute. Even if you don't have specific domain knowledge like Bill does about all of these detectors, I mean, I obviously have a cursory understanding now which helps me help Bill, but you can still go through those code examples earlier and see like that there's obvious problems to be solved. So, and then from the other end of things, often in physics, physicists and other scientists can be very, very resistant to asking for outside help. Like when it comes to things like third-party libraries, physicists like to have a lot of control over the things that they're doing, which is sort of why Bill found the canvas element and thought that was like, his sort of silver bullet. And the idea behind this is even if they're building a big, monolithic, unmaintainable piece of software, at least they know everything about it. So the idea of going to an open source project, or an established solution for databases like MySQL or MongoDB or something that in the industry we would know is tried and tested, the physicist or other natural scientists may have the impetus to be like, well, I don't want to put it in my code if I don't understand everything about it. So even suggesting like, hey, you're building a web app, why don't you use like a selector library, or why don't you use this bit of niceness? They don't want to put it in their code sometimes unless they can read through every line and know how it works. And so they'll just avoid it and try building their own thing. And I think it was Bill that was telling me about a particular instance in a physics library where they had decided not to use like a production-ready database that we would use in the industry, but they'd actually re-implemented their own version of ODBC, which was terrible. So they're kind of like repeating effort because there's like this fear of taking up too much time understanding these extra pieces. And it leads to this. I mean, I think that a lot of people that go through their PhD and are in the sciences end up kind of burnt out on a lot of this code stuff because they don't have any help and they don't actually know any better. And really, this is sort of contrary to the idea that science should always be a collaboration. So why aren't software developers collaborating with scientists? We've got this sort of barrier, this idea that because we're not professional scientists, or maybe I'm a software developer, because I'm not a professional scientist, I can't contribute to science. That's patently false. And physicists and other natural scientists that are coding and learning to code should probably be teaming up with people in software so that they can solve these problems more efficiently and do better science. So the question really is, how do we adapt our culture to do this with these sort of like cognitive biases in play?
This problem has to be approached from both sides of the equation, actually. And one of the most important things is, for programmers, is what Angelina has already touched on, and that's that the lack of domain knowledge in the science of your choice, whatever interests you the most, does not matter at all. We've got plenty of physicists to handle that. And as you can see, I mean, Angelina, just from some cursory conversations with me, picked up everything she needed to know about the Griffin experiment and its auxiliary detectors to be able to afford me the advice I needed working on this project. We started off by showing you those code examples and those user interface and user experience design examples to emphasize the fact that really what often needs help with is things that are very familiar to you, and it's the domain knowledge, not here, but out there in this audience and in the software engineering field, that's really, really at a loss for, and we really need to bring in. So one of the most important things you can do with your colleagues and friends and contacts in the sciences is educate them on the value of open sourcing their code. There's very little anyone outside the field can do for scientists as long as their code remains locked up in a black box somewhere. On top of this, encourage them to consider the fact that while they hold peer review very dear to their hearts, when the overwhelming majority of their results comes from code that no one can see, what does peer review really mean at that point? We need to start making science more open so that we can collaborate effectively on it. If you want to get a little more involved, this is sort of like a grading scale of involvement and engagement. The next step would be code reviews. Have a look once you get your scientist friends to open source their code. Have a look at it. See if you can spot any anti-patterns in it. Because as you can see from the code examples we started with, some of them are going to be really obvious and really simple for professional software developers. It would be just a few minutes to look at that and say, hey, have you ever thought of a for loop? Or have you ever thought of factoring that into a function? And it would make a dramatic improvement in this code. One step up from that as well would be make a pull request, refactor a little bit of the code to do things in a way that makes a lot more sense from a good engineering perspective. And, I mean, we don't expect you to solve our whole technical debt for us, that's silly. But one tiny example that we can learn from and take away can make a tremendous difference, particularly in the life of a student. Someone who's just learning, just in grad school now, learning how to code and how to deal with these giant frameworks of infrastructure. If they learn this early, just with a tiny example, they will take that away for the rest of their careers, and that effect ripples outwards. As you could see from my experiences in UI design, as I mentioned earlier, I mean, I have no training in user experience, obviously. Normally, when I interact with it, it feels a little bit like this. I tried my best, but I'm sure there's people out here that have even better ideas than I did on how to make physics experiments or experiments in any field as interactable as possible with a minimum of domain knowledge. Another element that we could use help with isn't just in software, but in our hardware infrastructure. So another sort of cutting edge element of Griffin is that Griffin will write 200 terabytes of data to disk every single week, and we'd like to analyze that in a day. Now, that's not an insurmountable problem, but it's an ongoing discussion right now of exactly how we're going to build a cluster to do that. And for some people, I mean, this might be a problem you've engaged with before. You might have some useful advice for us. We would love to hear your expertise on these matters.
So a message for scientists out there. I mean, I know that earlier, like you know, if this is being recorded, and if you heard the audience like giggle a little bit at the code there, like we're not showing you this, and we're not pointing this out to shame anybody, because frankly, at some point when I was learning software development and learning programming years ago, I wrote code like that. And obviously, the first example I showed you is code that Bill wrote. And Bill definitely writes better code now. So just to be clear, like this isn't to shame anybody. We just want you to do better. And just understand that if you're not a software engineer, then you are out of your domain. And you probably need to be accepting help or looking for advice. As Bill mentioned, and we really want to stress this, get your code in the open. So much code is written for these experiments, these simulations to verify results, and it literally is a black box. People will submit these papers for research, for publication, and go to conferences and do poster presentations, but they don't show the code with it. Nobody looks at the code. The supervisor involved, as long as the code at the end spits out kind of the right-looking example, kind of in the right-looking range, we just assume that it's okay, and that's a little bit of a problem, I think. Getting your code in the open really, really makes this a collaborative process, and it really makes science as open as it should be. So bring software developers and computing scientists on board, and preferably bring them on board early, because it will sort of have like a ripple or a butterfly effect. If you get some really good advice on making design decisions with how you do your software early on, then you can carry that through your project. And I mean, if you're in a situation at a lab where you can't bring them on early, bring them on to help you manage the technical debt that you have. That's better than not bringing them in at all. So and then the other one is, like I was saying, we're not trying to shame anybody. Just be okay with the fact that sometimes you write crap code. I know that when I'm prototyping something, like I'm prototyping a feature, I'll just be completely messy with it. I'll be like, you know what, I'm going to nest this like 6 times, and I'm just going to kind of get a result. And then like 2 days later, I go back to it, I'm like, what idiot wrote this? And I iterate on it, and I make it better. And one of the things I want to mention here is that over in the industry, we've sort of like, got this dichotomy of waterfall design versus iterative design, or waterfall development versus iterative development. And that's that, in waterfall development, you like plan everything linearly, and you sort of expect that everything's totally going to go smoothly, or not going to hit any roadblocks, and thus you'll end up with a perfect solution at the end. In reality, this pretty much never happens. So, I mean, once you do get something working, you need to be aware of the fact that probably your code isn't going to go into a vacuum somewhere, even if you are reasonably certain it is, because your supervisor might hand it off to someone else. And that, once you've written it, just go back to it and iterate on it and try and make it better. Don't fall victim to the notion that you writing it once is going to be enough for you. That's just not how good software is written. If you're a writer and you're writing a novel, you don't just go like, okay, first draft, going to send it off to the publisher. Guess that'll be okay. No, the editor will help you iterate on the process, and then your book will be published. The same can definitely be true for software. Because we like to pretend we all know what we're doing when we're writing software, but really a lot of us just fumble around kind of like this cat. So one particular philosophy I think that could really, really benefit scientists out there, especially when people are learning to code, is test-driven development or behavior-driven development, which if you're unfamiliar with it, it basically means that before you write your main piece of software, you get a testing suite, and there's some available for all sorts of different languages, and you write your tests first, and you describe the behavior that you want with your tests, and then you write the software so that those tests pass. And this has an effect in 2 ways. One, if somebody is unfamiliar with how to write really good software, you've kind of given them an itemized list of the things that they need to achieve. You've kind of said, okay, if you're going to write software to support the simulation, then here's the things that you need to do in order for things to be complete. The other thing that happens is when you do this, it sort of forces you to write really modular and decoupled code. When you're testing very small pieces of features, or you're testing really, really small pieces of a library, your code by nature has to become more modular, and more modular code is definitely more maintainable over time.
So just to wrap up here, before I came to Strange Loop, I talked to a lot of different scientists, not just physicists, because it's not just physicists that have this problem. I spoke to agricultural scientists and ecologists and life scientists, as many people as I could speak to. And the story was the same from every different field that I encountered. But the one anecdote that I wanted to share that was the most important was the one from the ecologist that I spoke to. I asked the ecologist, what would you do with more computing expertise on your team? And the ecologist said to me, the most useful thing that a software developer could do for me today would be just to sit down with me and have a conversation. Explain to me exactly what software engineering can do for me. Our fields have split so much. Software engineering has diverged so far from so many of the natural sciences that professionals in the field don't even know what to ask for at this point. And that technical debt, that ultimate cost of the extreme example of reductionism that we've gotten into is starting to seriously hamper our efforts to advance our sciences. We've gone very, very far in our little boxes, but now there is a tremendous amount of low-hanging fruit in the overlaps between our fields. If we want to start moving forward quickly again, those are the places we have to look for.
So when Alex Miller invited me to speak at Strange Loop, I actually had not heard of Strange Loop before, and I thought that was a bit surprising because I speak at a lot of technical conferences. But of course, I typed it into my generic search engine, and I looked up Strange Loop, and I saw some of the talks from last year, and it was immediately apparent to me what an interdisciplinary conference this was. Like, there's clearly a lot of people here from academic computing, there's a lot of people here from the software industry, and I knew that this was the talk that I wanted to give, and I encouraged Alex, like, oh, come on, I got to bring Dr. Mills with me, because we've been working on this for a while, and we really think that this is obviously really important to help better mankind and help actually produce better science with reliable results. So I was really, really glad that I could come here today and share this with this particular audience, because I think that you guys may be probably the most receptive to this idea. So, I mean, things are changing. A project actually cropped up where at CERN right now, a bunch of professional web developers, there's actually some friends of mine there, Brian LaRue and Remy Sharp, and not pictured, there's a really awesome developer that I look up to named Leah Veru. And they were actually brought into CERN to help recreate the original line browser for the web. And although this isn't CERN importing people to necessarily work on a physics experiment, they did go out of their way to say, okay, we want to recreate this important piece of web history. Let's get people who are professionals to do it. And that's something I hope that we see with labs and Attitude more and more. So this website, interdisciplinaryprogramming.com, tell your friends. If you go there right now, there's a very, very simple web form. If you sign up at the web form, all that happens is we're going to hold on to your email, and we're going to hold on to a little information about like how many people are scientists, how many people are software developers. And what Bill and I are working on is a platform to connect people in the sciences and connect people in software engineering and computing science together so that in the future, if you're interested in helping science, you can like go to that website and be like, you know what, I want to work with someone doing like quantum physics experiments. Oh, look, there's a lab that might be receptive to me helping. The idea being that we're kind of doing like a matchmaking service for both sides so that we can bridge this gap. And that project will be launching in 2014. So please take this domain and tell your friends, tweet about it. If you know people that are in grad school or working in an academic field, please tell them about it. We would love to hear from them, especially about their experiences and the kinds of things that they would need from a web platform like this. So in conclusion, thank you, Strange Loop, for having us here to sort of spread this message. You can find me as Angelina Magnum on Twitter, and Bill does physics, because that's what he does. And the slides will be tweeted afterwards if you are interested.
Thanks, everyone.